Hello, everybody. Welcome to the June 2020 monthly webinar. My name is Michael Kramer, and I am presenting to you on behalf of Perry Johnson Laboratory Accreditation. I am the Calibration Inspection Program Manager at PJLA. And as you can see, today's topic is going to revolve around Section 7.6, Evaluation of Measurement Uncertainty. We're going to look at those requirements, and we're going to look at some basic fundamentals that go along with these requirements and the general area concerning measurement uncertainty as it relates to ISO IEC 17025 2017. As always, this webinar is being recorded. You can go to our website and you can listen to this recording at a later date, or perhaps you have a colleague that may not have been able to join us. We also have the webinar slides. So if you just want the slides, you can also attend them. Excuse me, you can also retrieve them from our website. All attendees right now, you're in listening, you're muted, so hopefully everybody can hear me loud and clear. Cannot hear you. However, there is a tab where you can submit questions. So if something comes up during the course of this presentation, feel free to type your question in there, and at the conclusion, I will be able to review those questions. Please keep the questions in regards to today's topic, which is the requirements concerning measurement uncertainty, Section 7.6. So first thing I'd like to do is sort of in layman's terms, just look at what are we talking about with when we mention measurement uncertainty. So in a nutshell, it can be looked at as a doubt that exists about the results of any measurements. So you may take for granted that well-made measuring devices, perhaps measuring tapes, stopwatches, thermometers, should be trustworthy and give the right answers. However, there is, for every measurement, there is a margin of doubt. So it's a little gray area there. You can think of it as, in everyday language, give or take. For example, you might look at something and a rod, for example, and you could say, hey, that's a meter, give or take a centimeter. So that give or take is the uncertainty associated with the measurement of that rod. So since there's always a margin of error about any measurement, we ask, well, how big is it? Two numbers are really needed in order to quantify the measurement. One is the width of the uncertainty, and the other is a confidence level, which states how sure we are that the true value is within that margin. So, for example, we might say that the length of a rod measures 1 meter plus or minus 1 centimeter at a 95% confidence interval. Or this could be documented and written as 1 meter plus or minus 1 centimeter at a confidence level of 95%. So again, that 1 meter plus or minus, that's the value that we're uncertain by. And how uncertain are we? We're about 95% sure that that meter is within a meter, plus or minus a centimeter, with a confidence level of 95%. Go look at another term here, error versus uncertainty. So an error is the difference between the actual measured value and the true value. And the uncertainty is the quantification of the doubt about the measurement itself. So for example, we'll take a look at a 50-gram analytical test weight. Its nominal value associated is 50 grams. And you use this analytical weight perhaps to check the analytical balances in your laboratory. Send it out for calibration. It may not be exactly 50 grams. So you could see the actual measured value very close to 50 grams. However, it's correct. The error is 50.000112 grams. Hence, the 0.00112 would be the error. Reported, perhaps with an uncertainty reported of 0.000013 grams. So what that means is that test weight was measured and been determined that it's the actual value is, or you can say your correction is, a positive 0.000 or approximately 1/10 of a milligram, 1/2 from 50 grams. However, the uncertainty associated with it perhaps would be, well, if it's at an accredited calibration lab, it should be on the cal report, 0.00013 grams at K equals 2, or a 95% confidence interval. So I want to bring up the term traceability here. Of course, we have requirements in the standards concerning traceability. However, it does intertwine with uncertainty. Traceability, sometimes it's a term that gets tossed around loosely, but it's a defined meaning. So from the vocabulary of international metrology, metrological traceability is a property of a measurement result whereby the results can be related to a reference to a documented, unbroken chain of calibration, each contributing to the measurement uncertainty. So we have a clause, we see uncertainty associated there, and we also see the requirement in 17025 concerning metrological traceability. So the laboratory shall establish and maintain metrological traceability of its measurement results by the means of an unbroken chain of calibration, each contributing to the measurement uncertainty, linking them to an appropriate reference. So hence, if you're stating, or if you're looking at a report and it states their measurements are traceable, by definition, that includes the measurement uncertainty. So a chain of traceability exists when all the measurements are known and can be known for each link of the comparison, along with the associated uncertainty of the measurement. So ideally, we would have in the U.S., we like to say you're traceable through NIST to the SI unit. So ideally, the link at the back to NIST would be small. And each time you get further away down that link, you add to the uncertainty. Hence, each one of those links, if it was defined by uncertainty, would be a little bit bigger. Why? Because they built upon the links that were preceded them in this traceability chain that I'm attempting to depict here. So a broken link may be an instance, for example, that a measurement uncertainty was not estimated for the calibration. Hence, the traceability would stop at that point. So I'm going to look at the requirements here, and there's 3 clauses in there. They're kind of broad clauses in the standard under this section, just dealing with measurement uncertainty. Which is section 7.6, and clause number 7.6.1 states, laboratories shall identify the contributors to measurement uncertainty. When evaluating measurement uncertainty, all contributors that are significant, including those that arise from sampling, shall be taken into account using appropriate methods of analysis. So those folks that are accredited with PJLA, our policy on measurement uncertainty is PL3. And if you look at that definition, you look at PL3, heck, it sounds a heck of a lot like a measurement uncertainty budget that we have calibration labs prepare prior to getting accreditation and review them and change them as things change. So as you see there, and back before the standard was revised in 2017, there was a procedure that was required. When the standard was revised in 2017, no longer required to have a formal procedure. However, a procedure can still be used to incorporate the required elements that's specified in clause 7.6.1. So, necessary steps in developing an estimate of measurement uncertainty, or IE, starting an uncertainty budget. And this is a first step. Step one is you're going to look at all the contributors. Make a list of all equipment or conditions that would diminish the correctness of the measurement results. Second, we have to quantify them. So we have to give them a value. We have to determine reasonable values for the standard uncertainty for each identified contributor. Step number three is we have all these individual contributors. We then have to combine them. Combine all the standard uncertainty using the, as our root sum of squares method. We'll see how that's depicted here in the next slide. And we combine the uncertainty, and last but not least, we expand it. So we multiply it by the appropriate coverage factor, which typically you'll see that as a k equals 2, which is a 95% confidence interval. So we combine them, and then we multiply them by that k factor. So mathematically looking at this, we have the combined uncertainty. We square root each contributor. Each one of those U's are individual uncertainty contributors. And then we have our combined uncertainty. And then to expand it, we get the, we multiply it times the k factor, which is typically at a k equals 2. So uncertainty budgets. So with uncertainty budgets, the way I like to present it for calibration is typically there's always 3 contributors that would always be looked at. Hence, beyond that, it just pretty much depends on the type of calibration, the other sources that would be added to these 3. But these 3 sources are, you always have an uncertainty associated with the standard using calibration. That would typically come off the calibration report. And that would be divided by the k factor off the calibration report, which is usually that uncertainty divided by 2. Typically with all calibrations, you have an uncertainty associated with the limited resolution of the device calibrated. So this would be the actual smallest division which could be read under the unit of test. And that is a rectangular distribution. And we'll depict these a little bit in a little bit here, as far as what a rectangular distribution is and what it looks like. And that has a divisor typically of 1.73. And then repeatability. That's typically a normal distribution, and that's the standard deviation of repeatability studies performed by the lab. So again, the uncertainty of the standard, the first one there. So comes off the calibration report. So I have a sample here. We have a measurement uncertainty here. We have the K factor there, which if you can read the dissertation at the bottom there, you would take, if perhaps this temperature was a standard you were using to do temperature calibrations, you would take that measurement of uncertainty of 0.076 and divide it by the K factor. That would identifying and quantifying that particular uncertainty contributor. Resolution of device under test. So this would be the smallest division which can be seen on the unit of under test. So for example, if we're calibrating this device depicted on the screen here, and let's take, we'll see 23.4, that's degrees C. The next division up would be 23.5. So the smallest division would be 0.1 degrees C. So there's a little bit of uncertainty associated with that limited resolution. Where is the break point in it? That it would be considered a rectangular distribution and would be divided by 1.73. Repeatability, that was the third one we mentioned. So this would be a normal distribution of at least 10 measurements and would be the standard deviation divided by 1. Uncertainties are contributors are categorized as type A, type B. Type A evaluation involves evaluation by statistical or a series of results, i.e. the repeatability studies that we just looked at. Type B evaluation is evaluation by any means other than statistical. You come off the calibration reports, reference books, published values, experience, judgments, etc. So common sources of uncertainty. Got those three there that I mentioned that I would normally expect to see on every on the other uncertainty budgets, but below that, just depending on what the item is that's being calibrated. So that could be the uncertainty associated with environment. Perhaps you're doing air buoyancy corrections, or we have temperature, humidity, and barometric pressure. Uncertainty associated with equipment accuracy, drifts. So it could be calibrated, particularly electronics may drift between calibration. Uncertainty in regards to properties and condition of the unit under test, such things as uncertainty related to reflectness, hardness, the unit exhibits wear. Manufacturer specs could present some contributors to uncertainty, and homogeneity or uniformity. So perhaps we're in an environment where we're comparing a standard and an unknown. There might not be in the same environment, even though we're comparing one to the other, there could be some uncertainty associated with a difference perhaps in the actual temperature. So quantifying uncertainty. So there's several types of distributions are commonly encountered in estimating uncertainties. We're going to look at some 4 basic ones here. One is the normal distribution, has 1 standard deviation. You also have a rectangular. The normal with the 1 standard deviation is divided by 1. The standard uncertainty is rectangular distribution. 1 standard deviation is obtained by dividing the limits of the distribution by the square root of 3. We have a triangular where 1 standard deviation is divided by the square root of 6. And last but not least, I listed the U or uniform distribution. 1 standard deviation is obtained by dividing the limits of distribution by the square root of 2. So hence, here's just a sample of an uncertainty budget where the values were identified, identified and then quantified, and you can see they were combined, and last but not least, they were expanded. One thing I just want to bring up at this point is an uncertainty budget. When in PJLA, we're looking for uncertainty budgets to support your scope of accreditation. So when you look at a calibration scope of accreditation, that section that says calibration and measurement capabilities expressed as an uncertainty, that would need to be supported by an uncertainty budget. So that is it used to be BMC, best measurement capabilities. I like that better, but anyway, that would be the best uncertainty that a organization can produce. So when you're doing your uncertainty budget, particularly for an initial accreditation, you want to consider, hey, what is the best device we're going to calibrate? Of course, your standard should always be of higher accuracy than the unit under test. So for example, if you have a temperature standard of 0.001 degrees, you're not going to test an unknown that has that same resolution. So you want to at least perhaps go out to 0.01 degrees and then figure out an uncertainty budget, based on that. And that is a published CMC. So that is the for a calibration lab, that's off the scope of accreditation when you see that. or it could also come off of from the NMI, like NIST, for example, which is captured in the BIPM key comparison database. So again, looking at those distributions in a little bit more detail here. So the normal distribution depicted over there. 95% of the data points would be between the mean plus or minus 2 standard deviations. So this is typically encountered with uncertainty analysis, particularly with repeatability studies. Has a divisor of 1. And this is statistical, which is a type A analysis. Rectangular, which is not fully defined by the mean, and the standard uncertainty is defined as square root of 3 or 1.73. So the most common thing I like to think about here, it stays the same. It does not change. So we mentioned the resolution of the device under test. That's going to be the same regardless of where it falls within this distribution. So these are things such as resolution of device under test, perhaps specs out of a manufacturer specs that would be incorporated into the uncertainty budget would be examples of things that would be considered a rectangular distribution. A general rule of thumb, I'm just going to bring it out here. If you have a contributor, if you're not sure what distribution it falls under, most of the time it will fall under this one here, rectangular. We have 2 others, triangular. So you can see the depiction there. Most all the points are going to fall right there at the center. It has a standard uncertainty of 2.65. The boundaries, populations have finite boundaries, and elements near the center has a higher probability of occurrence. Common example I see associated with this is heating and cooling, temperature. There's you have boundary driven and you have center driven. So those folks with really good environmental controls in their laboratory, and it's much more expensive, of course, to have a center driven temperature controls within the facility. So the heating and cooling is constantly going against each other to keep the values very close to the center there. As opposed to the last one we're going to look at is U, where it's most of the distributions are going to be at the boundary. That has a is defined by the square root of 2 or 1.41, has finite boundaries, and has a higher probability of occurring at those boundaries, as opposed to center driven, you have boundary driven. So for example, if you have temperature controls, let's say 20 degrees C plus or minus 2 degrees C, the temperature would change as it gets closer to the boundaries. Say it's cooling down when it gets closer to the cooler boundary, then the heat would kick on there. So hence boundary driven as opposed to center driven. About uncertainty, make sure I didn't skip a slide there. I just want to also discuss random versus symptomatic variation. So random variation is where repeating the measurements give a randomly different results. So if so, the more measurements you make and then average, the better estimate you generally can expect to get. So examples of this would be posture change, effect to height measurement, reaction speed affecting time measurement, slight variation in viewing angles. What I try to depict there is reading a meniscus. Know what a meniscus is when you read a class graduate, you read it at the lowest point there. So folks see things differently. I was once involved in a class where we went around and we each wrote down how we were reading that. So people see things differently, but the more you read, the more statistical data that you collect, the better your average is going to get to the clear picture, excuse me, to the true value there, which you have a good depiction of that coming up. So random versus systematic, excuse me. So that's where the same influence affects the results for each of the repeated measurements, but you're not going to be able to tell. In this case, you learn nothing extra by repeating the measurements. Other methods are needed to estimate uncertainties due to the systematic effects. So examples of this would be, maybe you have a scale that just constantly is always off by the set amount. So no matter how much you use it, it's still going to be off by that set amount. Or a metal roller consistently giving different measurements when they're cold compared to when they are hot due to thermal expansion. Drifts occurs with successive measurements become consistently higher or lower as time progresses. For example, electronic equipment could be subjected to drift between calibrations, something you'll never see or be able to adjust for to. If you don't have to incorporate this into your uncertainty. So, of course, systematic errors are a bigger problem than random errors. This is because random errors affect precision, but it's possible to average multiple measurements and get inaccurate results. In contrast, systematic errors affect accuracy. Unless the error is recognized, measurements with systematic errors may be far from the true value and increases the chance of false accept/reject. So ideally, yes, and perfectly, we'd like to have the situation over there to the left, which is no error. We have accuracy and precision together. We're hitting the bullseye, and we're consistently hitting the bullseye. Random error depicted in the middle there. We're sort of centering it around the bullseye, but we're hitting the mark differently. However, the more readings we take, the average is going to better the chance it's going to be closer to the true value or the middle there, as opposed to systematic, which is over there on the right, which we're hitting a mark. We're consistently hitting the mark. Hence, however, that could be the wrong mark. So regardless of how much, how many more data points we collect, it's not going to offset the accuracy at all. We're not going to see it. We're just going to know that, hey, we're hitting the mark. We're consistently hitting the mark, but it's not an accurate mark. So you have to sort of look at that when you're looking at measurement uncertainties, including those into the budget or including them as a contributor. So under this section, section 7.6, the term estimation and evaluation is utilized. We see examples. So where there on the left, evaluation is a more strenuous, rigorous type calibration, which typically we'll see for calibration and uncertainty budgets. On the right is see a lot often with testing laboratories where we would perhaps the test method, as I have to find out here, precludes rigorous evaluation of measurement uncertainty, and estimation shall be made. And the evaluation over there to the left, laboratory performing calibrations, including its own equipment, shall evaluate the measurement uncertainty. So that's 7.6.2 concerning calibration. A laboratory performing calibration, including of its own, shall evaluate the measurement uncertainty for all calibration. So there we're identifying different contributors. We're quantifying, combining, expanding. Mentioned about including their own calibration, and we define this in PL2 for traceability. This would be, for an example, if you're a testing lab, and we do have some labs that do have in-house calibration, where we actually need to have a calibration assessor witness those to assure traceability. So part of traceability would be the uncertainty. So if you're doing in-house calibrations, bear in mind you have to evaluate the uncertainty of those if it's needed for traceability, and 762 would apply. All right, 763, there's only 3 clauses in here under section 7.6. A laboratory performing testing shall evaluate measurement uncertainty, where the test method precludes rigorous evaluation of measurement uncertainty. An estimation may be made based on an understanding of the theoretical principle or practical experience of the performance of the methods. So what are we talking about here? This comes right out of the standard. And these are notes. So in 17025, notes are just, I like to refer to them as FYI or just supporting information. They're not requirements. So note 1 states, in those cases where a recognized test method specifies limits to the values of the major sources of measurement uncertainty and specifies the form of presentation of the calculated results, the laboratory is considered to have satisfied that previous clause 763 by following the test method and reporting instruction. For example, rapid method kits that specify limits to the value of major sources of uncertainty, as well as recognized rapid methods where kits are used to determine qualitative results, would fall into here. Continuing for a particular method where the measurement uncertainty of the results has been established and verified, there is no need to evaluate measurement uncertainty for each result if the lab can demonstrate that the identified critical influence factors are under control. And there's some documents there. This note 3 comes right out of the standard for additional information regarding evaluation of measurement uncertainty for testing. We have 3 documents there. I also want to add, there's also an ILAC document who has a G document, it's a guidance document, G17, which is measurement uncertainty in testing. So if you're a testing lab, write that, you want some additional guidance on this, G17. And you can Google his ILAC, ILAC G documents. I do it all the time for guidance documents and P documents, which are their policy documents. So I have an example here of an uncertainty included in the test method. And this just happens to be from ASTM D 6184, which is the standard test method for separations from lubricating grease, and it's called the conical sieve method. So with this method, it's been determined with repeatability. So what repeatability is, basically the repeat measures, same person, same equipment, doing a measurement over and over. So repeatability, if this is the case, has been determined. The difference between the 2 test results obtained by the same operator with the same apparatus under constant specified operating condition on identical test methods, material, would in the long run, in the normal and correct operation of the test method, exceeds the value only in one case in 20. Which correlates to a 95% confidence interval, and has been depicted if determined through repeatability, 1.151 times the mean. Reproducibility. So this is basically, we have different technicians performing the same test using different equipment. So the difference between 2 single and independent results by 2 different operators working in laboratories on identical test methods, test materials would in the long run, in the normal and correct operation method, exceed the value only in one case by 20. So we're a little bit higher there, 1.5 0.517 times the mean. So hence that's been studied in this particular lab utilizing this particular test method. So what does this mean? So here's what it means. So we're following this procedure, ASTM D6184. Of course, we have a trained technician performing the test in all cases in accordance with the prescribed method, not deviating from it, consistently following the procedure. Under prescribed conditions, this method has perhaps environmental conditions such as temperature, barometric pressure, or within acceptable limits. Using specified equipment, not substituting equipment which may be performed differently than the test equipment specified. In a continued known of stated performance capacity. In other words, the equipment is in a state of calibration. You have it on an interval and hopefully stays within tolerance between calibrations. Can evaluate its results against the stated accepted criteria and then report acceptable or rejection against the stated acceptable criteria with a 95% confidence level. So again, we have acceptable criteria are developed by in-depth statistical analysis samples from multiple laboratories performing the same test. Sample data obtained from multiple laboratories performing the same multiple tests, test permits the determination of the mean of the distribution of the sample averages, i.e. the experimental standard deviation of the mean, and the standard deviation. This is used to establish acceptance criteria with a probability of 19 times out of 20 or 95%. Uncertainty is present due to the variation in equipment, operator skill, and reproducibility, but the manner by which the accepted criteria is determined includes the uncertainty in the method of the analysis and therefore does not require further analysis. So again, the summary of the test method, again, we're not deviating. So got to assure that the weighted sample is placed in a cone-shaped wire cloth sieve suspended in a beaker and then heated under static conditions to the specified time and temperature, unless otherwise required by the degree specification. The sample is tested at standard conditions of 100 degrees plus 5 degrees C for 30 plus or minus 0.25 per hour. The separated oil is weighed and reported as a percentage of the mass of the starting test sample. The sample is weighed on a balance, it's heated to a specified temperature, and it must maintain a specific temperature for a specific time. The sample is visually examined to detect non-homogeneity, such as oil separation, phase change, or gross contamination. So we have detailed dimensions with tolerances are provided for the cone and the wire mesh material of which it is constructed. A target dimension is provided to ensure that the amount of the sample material in the sieve is approximately the same each time. The sample is visually examined, i.e. by a trained technician, to detect non-homogeneity, such as oil separation, phase changes, or gross contamination. Specified, the balance must have a 250 gram capacity with a 0.01 gram resolution. Is heated to 100 degrees plus or minus 5 degrees. The sample is maintained at the specified temperature for 30 hours plus or minus 15 minutes. These potential variations were present during the statistical analysis, which developed the acceptable criteria, such as results. As a result, further evaluation of the measurement uncertainty is not required. So hence we have an example of There's many of them out there. And I want to just mention there is a standard, an ASTM standard, ASTM E2554. Often with testing results, it is based on repeatability, either repeatability or reproducibility. Could have a controlled sample in your lab that you're utilizing to capture this data. So this ASTM standard describes techniques for laboratories to estimate the uncertainty of a test result using data from testing results on a controlled sample. All right, moving on with requirements concerning measure uncertainty. So this is section 7.8, testing. So 7.8 is reporting the results. So we have different requirements here for testing. We have calibration and we have sampling. So this is in regards to test reports. And you can see where applicable, the measurement uncertainty presented in the same unit as the measured or the term relative to the measurement. When it is relevant to the validity or application of the test results. A customer instruction so requires it. The measurement uncertainty affects conformity to a specification limit. So it's not a shall there for all cases, just when it's needed for the interpretation of test results. So just have a couple examples of when it would be needed. Again, we have 7831C, and it is relevant to validity or application. And I think most importantly there, it specifies here a customer instruction so requires it. So if you're not sure, this is something that should be determined during contract review. So in the following examples, it would normally be necessary to report the uncertainty to your customers. If the laboratory is not required to report a statement of conformity. Environmental tests conducted regularly and where conformity to a specification limit is assessed by the customer. Such cases may be mandated by legislation or be voluntary in order for customers to assess if a parameter is subjected to change and possess a risk of not complying with the regulation. The measurement uncertainty needs to be known. The measurement uncertainty is necessary for the customer to make a qualified decision on changes to their water or wastewater treatment facility. Well, this states when the laboratory is not required to report a statement of conformity. We're going to talk about that here in a little bit here, statements of conformity. So if you're going to make a statement of conformity, you're telling your customer whether it's passes and fails, and we're also going to talk a little bit about uncertainty in the decision rule, how that would be incorporated into that decision. Another example would be product test, where a product is tested for conformity to a specification. In such cases, the lab results may be quantitative as well as pass-fail. In both cases, the reporting of measurement uncertainty should be important for the customer to assess the risk of product failure for an item near the specification limits. This is particularly relevant if the customer is the product manufacturer. And if unclear in whether or not the uncertainty needs to be reported for testing lab individuals, as per 7831, the customer instructs so requires it. So again, we're gonna have to go through during the contract review process prior to doing the test if it's not quite clear whether or not uncertainty needs to be reported. Moving on to 7841, this is calibration now. This section for calibration. And this basically say calibration certificate shall include the following: the measurement uncertainty of the results presented in the same unit. The measurements are a term relative to the measured. So when the standard was revised in 2017, this used to say, shall report the measurement uncertainty and or a statement of compliance. That and or went away when the standard was revised in 2017. So this is pretty straightforward. As per the standard 7841, that the calibration lab shall report the measurement uncertainty. No more and or a statement of compliance. So as per, and we're going to look at our policy PL3 on measurement uncertainty. A deviation from this protocol. It's got to be customer driven. Can't be shoved down the customer's throat. Hey, we're not reporting uncertainty. We're not going to report it unless you tell us. Any deviation from this requirement would need to come under the realm of simplified reporting. So that is under section 7813, which is you can report in a simplified manner. So anything that's under 7.8, which is reporting the result, for whatever reason, the customer does not want one of these required elements in it, they could come under the realm of simplified reporting. The caveat, though, would be that you have to be able to go back and duplicate the required elements that were left off. And this would only be permissible if agreed to by the customer during the contract review. And this comes out of PL3. This is our policy. And this shall be documented. So unless otherwise specified under for calibration, the uncertainty is required to be put on reports. And if it's not, it has to be customer driven, customer specified, and a record needs to be obtained during contract review. Excuse me, have to be created during contract review. To have that agreement in writing. However, if need be, you would still need to be able to go back and duplicate the duplicate the save enough data where it need be, go back and ascertain what the measurement uncertainty would be. And we're going to talk about the decision rule there. This would not also alleviate the customer does not require measurement uncertainty, does not alleviate the lab's responsibility for the decision rule as well. We're going to get to that here real shortly. So 785 is in regards to sampling. So we do have sampling organizations, or perhaps you're a testing lab that you are actually going out and collecting your own samples. Uncertainty would be needed for that for the sampling. If it's that uncertainty is needed to evaluate subsequent testing or calibration. All right, decision rule. This is comes into play in reporting, and it's a definition that's in the standard when it was revised in 2017. So it's the rule that describes how measurement uncertainty is accounted for when stating conformity with a with a specified requirement. And here's the requirement there. When a statement of conformity to a specification or standard is provided, the laboratory shall document the decision rule employed, taking into account the level of risk, such as false accept and false reject, and statistical assumptions associated with the decision rule employed, and apply the decision rule. So a decision rule, of course, it does include, it incorporates uncertainty in there. Well, if you're not sure what I'm talking about here, when you make a statement of compliance, that's where you're saying something passes, something fails, something's in tolerance, out of tolerance, whether you're reporting it in a sample, in a test or a calibration. So I try to depict here under 4 different scenarios here. We have the red line there is a specification. That's the line in the sand there, or where we're saying an item that we calibrated or tested was within a specified tolerance. So that red line above that is the upper spec. Below that, the red line below it is the lower spec limit. So we have a data point there indicated by the dot there. And we have that gray area of measurement uncertainty that surrounds that dot. So category 1, we see the value and we take into account measurement uncertainty. It's all below the spec limit. So we can safely say with a say K equals 2, 95% confidence interval with our reported uncertainty that's a pass. As opposed to going from left to right, category 2 and category 3 there. Category 2, the value actually passes. However, the uncertainty creeps up over to the spec limit. So it may not be a pass after all if you take uncertainty into account. Or in the other case 3, it could barely fail, but it may not fail when you consider uncertainty. And category 4, that's a clear failure. So the value itself with the uncertainty incorporated into it is both above that spec limit. So again, the decision rule is how you take measurement uncertainty into account. There's various means of doing that. You also will need to, as per contract review, section 713, clause, even prior to reporting uncertainty in the decision rule, you have to gain the customer's agreement as to the decision rule that you're going to use. Still under here, 7862 still incorporates the decision rule. The laboratory shall report on the statement of conformity such as the statement clearly identifies the decision rule, unless inherited in the requested specification or standard. So what are we referring to here? And just have a couple examples here. One example is ASTM E18 for Rockwell hardness, where the testing decision rules takes uncertainty into account in the repeated testing and other limits as to the spread of data, and the rules are defined in the methods. Another example, ASTM A29 for standard specification of general requirement for steel, barred, carbon, and allied hot wrought, where it has an auxiliary table that is based on the method. Uncertainty to give some extra room to make a decision. Many others, there's 2 as far as the proposed question there, unless inherited in the requested specification. I mentioned guidance document for uncertainty for testing. There's also a guidance document for decision rules, which is ILAC G8. There's guidelines. It goes over this guidance document has been prepared to assist laboratories in the use of decision rules when declaring statements of conformity on a specification or standard as required by 17025, 2017. The standard, of course, recognizes that no single decision rule can address all statements of conformity across the diverse scopes of testing and calibration. Keep in mind with your decision rule, and I have a copy there of, I have documented there 713. When I'm doing an assessment, decision rule comes up in 2 places. It comes up in 713 during contract review. So that's how you take measurement uncertainty into account. The decision rule, if you recall, that's a definition. And you see the requirement. We see the decision rule selected shall be communicated to and agreed to with the customer. All righty, so that concludes the presentation. If you bear with me a moment. While observing some accredited certificates, it was found that some laboratories are reporting same uncertainty to all measurement points. Is it acceptable to report preset uncertainty values without actually calculating uncertainty each calibration point? Or are they computing repeatability, reproducibility, resolution? I really don't know that just by looking at the report. I can tell you this though, the uncertainty is required to be reported. Each calibration, the actual uncertainty reported should be based on that particular calibration. Should be nothing that's preset for the entire calibration. Two things will change. One is the resolution of the device under test. So what's published on the scope is a CMC. That would be the best. Repeatability would be different. I give an example of like a pipette. You buy top line pipette directly from the manufacturer, or you go get something that's 20 years old with worn out seals. Your repeatability is going to be better with the better pipette than it is with the worn out one with seals. So those two things will tend to change. You can report one blanket uncertainty on a calibration report. There is a requirement when you report uncertainty, you can always report one higher, but never lower than what's on the stated the stated scope of accreditation. Hence, if sometimes there's not a whole lot of difference between the low end and the high end, and a lab can report one blanket uncertainty just as long as it's the highest one throughout the points that were taken in the calibration. Can you explain a little bit about uncertainty related to regulation of digital and analog devices? Only thing with a digital device, it is actually permissible to do it's escaping me at the moment. You can increase that divisor if you can do some additional studies and actually find the break point. An example of this would be like in the scale industry. I mentioned if you have a scale that reads to, let's say 100 milligrams, you can do what's called a discrimination test, where you can see if it's within that half interval or not by adding additional test weights to it and trying to find where that break point is. If you're just looking at the whole resolution at once and you're unable to do any further testing, then you would not be able to incorporate lowering that through further testing. How can manufacturer specifications be used in evaluation? Again, it totally depends on the device that we're talking about. One thing that's commonly I see with electrical calibration, there is an accuracy requirement that's typically covered in a under manufacturer specification, which is drift. So between calibrations, the item may drift. So unless you have additional enough data on the item, you would have to resort to manufacturer specs to ascertain that, to quantify that uncertainty contributor. After a period of time, perhaps you have a device that you send out every year and you have data behind it and you can support, hey, this device is rock solid, and you may have a little bit more confidence as to be able to ascertain your own value for that element of drift as opposed to um, uh, utilizing manufacturer specs. Yeah, this one here, and I've been getting into all this detail. This is a broad overview of measurement uncertainty, and I used a value of 10 here, which is typically for repeatability. Someone had attended a PJLA webinar, and the K value was depending on the number of reads. So with that, you would use like I said, this is a 1 hour webinar. Didn't get into all that, but there is a T distribution table that would base your K factor on the number of your sample size. So the bigger the sample size on your repeated readings, then the lesser amount of the K factor that would correspond, and that's from the student T variable table. Yeah, and the rest of that, is it based on the student? I'm reading the rest of this question here, and do you still have that? Yes, I do. I actually I gave that out, and that course I believe was probably a day, at least a day long, where we it was a live course. It wasn't a webinar, but yeah, we still have that presentation, and we haven't actually. We're looking at we haven't done live training for COVID reasons mainly, but I'm hoping that we can get back into doing some public type workshops and be able to uh, do live training again and more detailed training. But reading some of the rest of these questions, I'm trying to make sure I'm capturing the gist of it. Could I share this presentation? Yes, if you missed the first part of the webinar, this is being recorded. www.pjlabs.com. Go to our website. There you'll see the tab for webinars. You can actually get the slides of this presentation, or you can get there. You can go and actually get it goes on YouTube. It has a link. It will take you, or you can go back, and there's a lot of information. It goes back several years. Recorded webinars, so you can get it from our website. You also plan the training on the evaluation of intercomparison. Not sure what you're for intercomparison in regards to proficiency testing is what I'm thinking you're asking there. I'm trying to think. Did a webinar not too long ago on the requirements for PL number 1, which is proficiency testing, and we went over interlaboratory comparison. What was the ASTM method again for uncertainty? I'm assuming you're referring to the uncertainty for testing, which was ASTM E2554 that describes techniques for laboratories to estimate the uncertainty for tests using data from test results on controlled samples. And I'm a calibrator. And I don't want to steer anybody wrong. I have some specific technical questions in regard to testing. I'm trying to. And just based on this presentation here, this person is asking, they're a testing lab, not a calibration lab. What is the best way to determine the uncertainty of the internal test method? So I'm assuming you wrote your own test method. Is it sufficient to do a repeatability study based on 2 or 3 replica, 3 or 4 times, and then use a different standard deviation to calculate the uncertainty for the test method? I would, that sounds like a good plan of action. I don't want to steer you in the wrong way, wrong there, but test, particularly, if you have a controlled sample or if you have a good reference value, maybe from an accredited reference material producer, maybe base it on that where you have a good reference value and you can, get your repeatability and any sort of bias that could be built in it. If you have a reference value, treat that as the unknown and then see if you get any biases among your technicians. Could you please clarify the figure for uncertainty in decision rules for conformity statements? Again, G8, I'll refer you to that. It goes into a lot of statistical data. I mean, again, with the decision rule, the customer has to agree with it. A decision rule can be anything from something called simple acceptance. Again, this would need to be agreed to from the customer, but statistically, that is just taking the pass-fail in regards to the recorded reading without taking measurement uncertainty into account. The possibility of false accept or false accept in that case would be worst case scenario. If it's right on the line, it could go 50-50 either way. That would be up to 50%. And then it will take it from there. Typically, yep, you want to take it into account. And typically, most of the time, you're guard banding against it. If you're doing a 95% confidence interval, you're not going to say something passes and fails if uncertainty actually affected it. Sort of like that diagram that we had earlier in the presentation. In that case, worst case scenario, if it's right on the line, if you think about it, if you're having a 5%, it could go either way. So the worst case scenario in that instance would be 2.5%, because it could go either way. This individual is asking about triangular and uniform distributions. Triangular, most everything would be at the center, right at the mean, shaped like a triangle. And uniform is at the boundaries. That's at the U. Excuse me, that's the one that looks like a U. And the example I gave, you're asking me again, what were the examples? Would be like heating and cooling, center driven, where all the values, if it's center driven heating and cooling, it would be around the middle there, because heating and cooling are fighting against each other. It's more expensive as opposed to boundary driven, where the heating or the cooling element will change right when it gets closer to the boundaries. Whoop, sorry, I lost my place. It's optional to take the uncertainty in the decision rule. I'm not sure what the gist of that question is. One thing with the decision rule, if you're not making a statement, only if you're making a statement of compliance, the decision rule comes into play if you're not making a statement of compliance. Let's say you're doing a certificate of analysis for a sample if you're a testing lab, you're just giving them the data. You're not saying pass fail. You don't need to have a decision rule. It's not required. That's only when you're making a statement of compliance. And same with calibration. If you're reporting a value, of a device or correction factor with a degree of uncertainty. If you're not stating pass, fail, intolerance, out of tolerance, then you're not making a statement of compliance. Hence, a decision rule would be an NA, not applicable in those cases. Did we need to take all contributors mentioned in the international standard? Not really sure the gist of that question. You have to take into account all significant contributors. So bear in mind, I mentioned those three, and there that I would expect to see in all uncertainty budgets. Uncertainty is standard, repeatability, and uncertainty associated with limited resolution of the device under test. From there, it depends on what's being calibrated. I'll give you an example. Pipettes, I know temperature affects that because you're making a correction to a specified temperature and you're converting mass to a liquid. No, excuse me. Yeah, mass to a liquid. I'm sorry. So I would expect to see an uncertainty associated with that temperature, for a pipette calibration, for example. If I did not see it, and you would tell me that it was insignificant, then the ball would be in your court. And I'm speaking as an assessor when I say that, if I'm trying to give you an example there. To sort of back that up, what were you considering when you did not consider temperature, and how did you consider that as not being a significant contributor? Talk about like scales. Scales go anything weighing device from a truck scale to an analytical balance in a tightly controlled lab. You're going to have more considerations than say a micro balance that's reading to 1/100th of a milligram, as opposed to a truck scale that reads in 20 grams. So, however, you're still going to see those three elements, even with a truck scale. Often you do repeatability. There is a standard written for those type of devices that allows you to take repeatability based on scale resolution for various reasons. All righty, I'm starting to get a little tongue-tied there. A lot of good questions there. A whole lot. I know this is an area that a lot of, unfortunately, I have a large group here, got a large, and again, thank you for, there is a lot of attendees here because this is a topic of interest to a lot of folks. Particularly, I can speak for calibration when I do an assessment for an initial calibration facility. Then uncertainty budgets are one of the big stepping stones, one of the hurdles that a lot of folks just getting into this need to overcome and need to understand. So again, if you excuse me, you can if a question went in unanswered, and it was a couple I just really didn't know because they were industry specific, type it in, send it to that. If I'm not sure of the answer, I will send it to the folks in the testing program manager. Perhaps it can sort of give you, I don't want to steer you wrong, give you some more informed guidance. So before I let everybody go, appreciate everybody signing in. Next month, July 25th, we're going to have our next webinar, and it's going to be on complaints and overview of the requirements, Monday, July 25th. Again, thank you, and look forward to seeing everyone or logging in again in July 25th. Mark it on your calendar. Good day.